Okay, let's try this going. Phosphorus, how many around it? How many Lewis dots around it? Focus, children, up front, please. It's 5. Okay, how many around an oxygen? 6. Good. Okay, we have 1 phosphorus and 4 oxygen, so I know right up front that the phosphorus is going to be in the center. So I put it in the center because there's only 1 of them. And I say, okay, I can put 1 oxygen right here and do that coordinate covalent bond. And it's fine. And I've got 3 other oxygens, so I know they're going to have to come around here. This one's not fine, it needs 1 more. This one's not fine, it needs 1 more. And this one's not fine, it needs 1 more. But I have 3 extras, so they're going to come right here and come in. So I would write P, O, 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 and I would put all the extra dots around them. And I would put the bracket around it and say I added 3. Yes?
On the oxygen on the top, wouldn't there be 2 lines there?
There wouldn't be because oxygen needs 2 and phosphorus is contributing both of them. So there's just 1 bond, but phosphorus gave both electrons to that bond. Okay? All right. And if we go around each of them, we would see that they all have 8. We circled each one of them and go through. Okay, so let's go to nitrogen. Nitrogen has how many around it? Good. And hydrogen has 1, right? So nitrogen's going to be our center. And we have 4 hydrogens, so we're going to bring a hydrogen in here, hydrogen in here, and a hydrogen in here. Now a plus means I gave up an electron. That's because the other hydrogen just comes in here, but it doesn't bring its electron. It gave it up to somebody. So we put brackets around it, and we put a plus. Or we could write it like this, with the bracket and the plus. Okay?
Oh, is it? And then that's just 1 line to all 4 H's.
Right. But I did it with the dots. I probably should have used another color besides blue and black, but the one from the top hydrogen is sharing both the top nitrogen's electrons. It didn't bring its in. Okay, so we're going to bring this down and go back to our exceptions to the octet rule. So we've been saying octet, everything needs 8 around it, or for hydrogen and helium it needs 2. Well, there are exceptions to the octet rule. One of them is boron, and the other one is PS by the way they get it their way. So phosphorus and sulfur. So on boron only has how many around it? 3. So if boron only has 3 around it, it's going to go in a triangle. Okay? And because it goes in a triangle, it's actually going to bond up with fluorine, over with fluorine, and over with fluorine. But I can't leave it like this because I'm showing a dot and then a line, and that's not what we need to do. So we just change it like this, and then we can show the other 6 around each fluorine. Okay, would you do boron trihydride, which is the one on the upper right? Use what I'm doing and show it.
Wait, so how can the fluorine have 1?
Fluorine only needs 1. Fluorine only needs 1. So if I did the Lewis dot for fluorine, it has 7. And boron, if I did it for boron by itself, boron has just 3. It hasn't opened up that 4th room. Because it hasn't opened up that 4th room, it can't have 8. Okay? So over here, when we did the boron trihydride, it would just be, and we're done. Okay? Now I'm going to do the sulfur hexafluoride right here. P.S. by the way, these ones are like the party animals of the periodic table. The more the merrier. So if we do sulfur here, sulfur has 6, and fluorine needs 1. And fluorine is extremely aggressive. And it forces sulfur to give every single one of its electrons up for a bond. So what it looks like then is here's all sulfurs. And here comes a fluorine to bond here, 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 and to bond here. Now this doesn't give you the overall what it actually looks like. So I didn't put all the other extra dots on fluorine. So what actually happens is sulfur is the center. There's a fluorine on top with its 6. There's a fluorine on the bottom with its 6. And then on a plane here off of, one's going out and one's coming out of the table at you, one's going back in. There would be a fluorine right here and a fluorine right here. So if we were to look at this in a 3D model, what it would look like is a piece of paper, and you would take a pencil and go right through it. So this would be my sulfur, and my fluorines would be out here and up here and down here. So this shape is called octahedral. Okay? I want you to try and draw what you think the PCl5 would be like. Alex, put it away, please. Okay? So try and draw what the PCl5 would look like.
That just totally works out.
Okay, got an idea? What it might look like? Yes?
Would it be like a triangle with a pencil going?
It would be. It would be like a triangle with a pencil coming through it. So if we were to draw it over here, it would be phosphorus with a chlorine on top, like this, a chlorine come off the bottom, like this, and then at the center you would actually have the triangle of the chlorines coming out, where each chlorine on this plane would be 120 degrees from each other, where this one over here, all of them are 90 degrees from each other. Okay? All right, so exceptions, boron doesn't have enough. It only gets to 6. Exceptions, phosphorus has 10. Exception, sulfur has 12. So they get a little crazy. Okay, so I went backwards. I didn't go forwards. Come on. All right. We need to talk about resonance. Resonance is putting things together so the bonds are in different places. It's a hybrid of the two structures that you could possibly make. And we're going to make some hybrid structures here in just a second. Resonance stabilizes a molecule by spreading out where the lone pairs could be or where the double bonds or triple bonds are. A molecular ion that has 2 or more resonance structures is called a resonance stabilized structure. Okay, going forward, we okay? Now, to be able to draw a resonance structure, you sort of need to take everything we've learned so far and put it together, put it to use. So I'm going to walk you through this first one, but then you're going to do these last two. This one should have been O3. The first thing that I would do when I have to draw resonance structures, I look at the Lewis dot for each of them. So hydrogen has 1, right? Carbon has 4. And we have 3 oxygens that have 6. So I've got 3 of these. Okay, so I'm going to actually draw the 3 real here because I'm going to cross them off as I use them. That actually helps. So as you look at this, first of all, you're looking at one that would make the most bonds. So as I look at that carbon, hydrogen, and oxygen, which one could make the most bonds? Carbon. So I'm going to put that in the center. And if I put that in the center, I can say, okay, if I have carbon in the center, it has 4 dots around it. But I know an oxygen actually needs 2, right? So if for one of these I take one of those carbons and put them together, I know I can satisfy one of those oxygens if it will share 2 with it. So I can cross out an oxygen, I can cross out the carbon. That still leaves me 2 oxygens and a hydrogen. If I put one more oxygen right here, I'm still going to be short by 1, right? But I've got this hydrogen here I can plug in. So I'm going to take that hydrogen, I'm going to plug it right there. So now I've taken care of another oxygen and the hydrogen. Okay, well I've got one more oxygen, so I'm going to put it in right here. And when I put that oxygen in, I'm still going to be short 1. Are we okay with that? But, look, that means I had an extra one. So I'm going to take that extra one, and I'm going to put it right here. Now I'm going to transfer it into a line diagram one, where I can say, okay, here's my carbon. It's attached to an oxygen, which is attached to a hydrogen. This has 2 unshared electrons on it. We have a double-bound oxygen, which has 2 sets of unshared pair of electrons. And I have a single-bound oxygen, which has 3 unshared pairs of electrons. It has an extra electron. This is one resonance structure. If I take now and I redraw this, and I say, I'm going to switch these 2 places, I can then say the carbon has a double-bound oxygen on the top with 4 extra. Over here it has an O with an H attached, and over here it has a single-bound oxygen. It does have 1 extra electron. These are resonance structures. It's not that I've just turned it in space, because if I turn this and try and line it up, it wouldn't line up. Okay? But I've actually flipped these 2 places. And because I flipped those 2 places, I've got a resonance structure. Okay? I want you to try and do it with SO2 and O3. Yeah. I'm leaving that up there. I want you to try and do it with SO2 and O3. Okay, don't look up unless you get frustrated or you've got it done and you want to double check. Whoa, hello. Oops, too many. Okay, the only difference between the SO2 and the O3 is I replace the S with an O. So this would just be, whoops, see, I want to put the O, the S there. And it would be a resonance structure with that's 2 dots over there. Okay, so I can't just rotate it and put them on top of each other. It actually flips positions. So when we look and we actually do tests for ozone to see how long the bond lengths are, it actually shows its bond length is 1.5 bonds.
You said this was easier.
This is. Okay, so resonance just means I can draw it 2 different ways. Okay, that's all resonance is. So, how do we use covalent compounds in life? Well, we use them in our heart, especially. There's all through our bodies, actually. But in our heart, glycine is a building block for the protein that composes the heart muscle. We've got nitroglycerin that acts on the blood vessels to help it squeeze and go back and forth. We've got protein hemoglobin that's also covalently bound that has that, what?
Did you say nitroglycerin?
Nitroglycerin,
Like the same stuff as the explosive?
That's why they have nitro pills that people with heart problems, they just put the nitro underneath their tongue. The most part of our body is water, and water is a covalently bound compound. This picture is actually in your book, and so when you go do your Learn Smart, you'll see it again, and you can write down more stuff here that has to do with that. Going forward, we talked about ozone on the last couple pages ago. Ozone is something that is covalently bound, and it is important to the Earth as far as the ozone layer. We actually have holes in our ozone layer, and the ozone is important because it stops too much UV radiation from getting down to us. And actually, if we find ozone down on the Earth with us and not above the troposphere, it is actually a pollutant. It actually causes problems. We do use ozone, though, to neutralize bacteria and viruses, which is sort of interesting. So that's just some things that we've been using them for. Hold on. Yes, Luke.
I've actually heard the holes in the ozone have stitched themselves back up, basically.
It depends on the time of year you're looking at them. So with the Freon not being as released anymore as it used to be, because the old fridges had a lot of Freon in it, and when the Freon got free, ozone is a radical of oxygen, and when the UV rays hit it, it goes back and forth between oxygen and ozone, kind of thing, going back and forth. But we've changed to a new product which doesn't have as many fluorines and chlorines in it. And so because it doesn't have that in it, that has stitched back a little bit. But it just depends on the time of year and how much pollutant is in the air, if it's gone or back or worse. So it's been interesting to watch. There's actually some websites that you can get up on and sort of watch it, how it progresses during the year. Okay, so here's my big caution on this. We're going to learn how to name type 3. Type 3 is probably the easiest thing to name that there ever was. However, once kids learn how to name type 3, what I call type 3, which is non-metal to non-metal or non-metal to metalloid, they want to name all compounds this way. You cannot name all compounds this way. It must be a non-metal to a non-metal or non-metal to a metalloid, which is that upper section of the P. not including your noble gases. So there's not very many, and there can only be 2. If there's 3, this naming does not work. Only works with 2. Okay, so very, very important. So as we look at this type 3 naming, we are going to be using prefixes. You guys already know how to do this. CO2 is called what?
Carbon dioxide.
Carbon dioxide. CO is called what? Carbon monoxide. What are you doing? You're putting the prefix in front. Do you put mono in front of the first one? No. You only put mono if there's one of the second one. So you're going to be using these prefixes. So these are basically the same as math except one. Which one is different from math? Tetra. Tetra. In math you use quad, right? Quad means 4. But in chemistry, we use tetra. So I think Tetris. Tetris is 4 pieces of block put together in different shapes.
Like which one's Greek, which one's not?
I have no idea on that one. I don't. That's something I don't know. Okay, so we're going to be using these prefixes. Hopefully you've got them written down. Again, my biggest caution, and I keep saying this before we actually go into naming this, you can only use this to name 2 elements that are on the diagonal or above, okay, in the P section, not including the noble gases. So that limits what you can do here. So this is really simple. Dinitrogen pentachloride is N2Cl5. You see how that works? Okay, so what would the name of the next one be? Diphosphorus. 5 is what? Penta. We drop the A because the A and the O don't go together, and then we just put oxide. So if there's 2 vowels together, we'll drop the end. Okay, carbon disulfide. What would it be? Okay, N2Cl5. Cl5. Pentachloride. Good. And the bottom one? CO2. Okay, so this should be really fast. Now, I'm going to give you each a number. We're going to put them up as fast as you can. You're going to see if you can get all the way through before we get them all up here on the board by yourself. But you're going to put the one up that you're reassigned. Okay? So here we go. Here we go. Do them as fast as you can. You got 1. You got 2. You got 3. You got 4, Luke. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you got to make it all the way to 14. We'll show 10, and then we'll go to the next slide to do the 14. If you get through that, see how far you can get before we get all of them up. So there can be 2 writing at the same time. Oh, I've got the other thing. Yep. What? So 1 through 10's on the board right now. Once they get filled, I'll let you look at it for a minute. Then we'll go on to the 11 through 14 on the next page. UO. Try and get down to 14 before everybody gets all their stuff up. And go past it if you can.
Is this a magic eraser?
Uh-huh.
These things are so magical.
They're awesome.
You get them just a little bit wet too.
Oh, yeah. They clean up everything, except they didn't take my ink off my ink pad.
Oh, I have failed. I need to fix that with the U in the middle, please.
Phosphorus. Oh shoot.
What do I erase?
Fist. It doesn't like your fist.
Oh, it's because my marker's on the board.
Oh.
boxes or those pressers?
I do.
What are you using those for?
Tonight.
I'm gonna have to trick or treat your house and call it good.
Okay, these are all correct. So if you want to double check real quickly, did a good job on the first page. We'll see, turn the page here in just a minute and see what we did on the second.
We did this everything?
On numbers we did. Numbers I passed out.
No, I mean like, I never got my.
That's what I'm saying. It's on the next page. 1 through 10 is up here. If you got a number past 10, it's on the next page.
So I'll have a chance to write it up there?
Right. Okay. So 1 through 10, double check. Make sure you got it right. And then I'm going to go to the next page. It's looking more Halloween-y outside. Okay, I'm going to go to the next page. If you had something on the next page, come on up. I'm going to add now. I ended with number what? What was my last number? 14? I'm going up. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 26, 27. Wahahaha. He'll be 28. 28.
Is it fluoride?
6 hexa. I'll put a hex on you.
Would it be chlorine or chloride?
If it's first, it's chlorine.
So, mine was.
Sorry I gave a short person the top row. Didn't mean to. Go as fast as you can. See if you can get more of them done.
So if the one that you gave me isn't up there, you can wait?
Right. So you just wait. So get all the others done up to where you're at.
Is bromide just 2-bromine dibromide? That's 2-bromine, right?
Dibromine has 2 bromine. Yep.
Why can't all the names be like this?
This is, I didn't make the naming systems. I'm just teaching you them.
This would be so much easier if this was all the names.
But, yeah. The problem is when you had the ones in the center, they have more charges. There's no way to tell what charge you're using. So that's why. Okay, let's look at these real quickly. The first one is right. Second one is right. I think that's supposed to be a 5, not 15, right? Okay, I'm just going to put the 5 down there. Okay. Next one, yes. Next one, yes. It's dichlorine. You only put the IDE on the end. So number 16, this fluorine needs to be changed to fluoride. The last one always has an IDE. Bromine pentafluoride, bromine dioxide, and dibromine monoxide. Yes, so these are all correct. Did anybody have any questions on any of them? How did I fix that one fluoride? Okay, next group, you're up. So if you got one on here, get it up. Good. Yay! Told you this one's easy.
Yeah. Aside from the bonding part.
You got another bonding too. No, it's not hot.
You're right. I want to get one of these things for my room. It's kind of cool.
It is.
It is so
Wait, all
hard
of
to remember.
the last words always end in ID.
Right, IDE. That tells me it's the most electronegative or the closest to fluorine.
What's the deal with mono? Do you have to?
Mono, the only time I use it is on the second element. If there's only one of the second element. I don't ever use it on the first one.
You guys should rewrite mine so it's a little bigger.
Ah, you're fine. You really wanted it bigger. All right. I think you're getting it. Yes? Pretty easy, right? There are some more that you can practice with, so I'm not going to do them all today with you, but you can practice more of them at a later time and double check with your partner. So we're going to go through these really quickly, and we're going to go on to shapes. So if you'll get to the bottom of that area, there is a place where we start talking about shapes. When we're talking about covalent molecules, because they're sharing and they're not electrostatically attached like ionic is, we actually get shapes of molecule. A linear would be one that just has two that it can share. It would be 180 degrees. So you have two, you have little balls and stick think models there. If I have three, they're going to get into a 120 degree angle, and we call it trigonal or trigonal, however you want to say it, if you're from the east-west or the east or the west coast, planar. This is still in a plane. It makes a triangle, but the angles are 120. So it's like a circle. You just split it by 3. If I get to where there's 4 around it, I've now gone into a 3D model. This is where I'm going to have 109.5 between all the angles. All the angles are the same on this. And it is called a tetrahedral. If in that tetrahedral, instead of having an atom on the top, I have an unshared pair of electrons, what happens is this unshared pair of electrons, I think I've told you before, I call it a ghost because it scares down the others and it actually pulls nitrogen out. So what happens is nitrogen now is pulled out of that plane. It's now not sitting in the plane anymore. And because of that, we get a 107 degree angle. So the ghost scared the angle down by 2. But the name of it now is a trigonal or trigonal pyramidal molecule. And because of that, there'll be some issues we'll talk about in a few minutes. If I have 2 unshared pair of electrons, remember I warned you about this shape being drawn this way because it looks linear, right? But I've got to remember this is not linear. There's 4 things around that center molecule. And the 4 things are going to be in this shape for the most part. But 2 of them are the ghosts or the unshared pair of electrons. So the actual shape of the molecule is bent. It is not linear. And they'll try and trick you on that one. So you need to be really careful on that one. The angle is 105. So it's not a 90 degree angle, but a little bit bigger than that. Okay, so we need to know these Vesper shapes, these basic ones. You also have a chart down below that has all of them on it. There's some things that you need to fill in on that chart, so make sure you're filling them in while I'm talking to you about them. The first 3 rows we've just talked about. We have talked about the different shapes that could possibly be. The only one we didn't talk about is on the number 3 where it says bent. That bend is actually a little bit bigger than 105 degrees because of the way that that works. Because this angle right here was 120. So if I put an unshared pair of electrons right here, this angle right here is just under 120, so it's like 118. So it's a little bit different bent, but it's still considered bent. These bottom 2, this is where we had our phosphorus. This is where we had our sulfur, where we were at the trigonal bipyramidal and we were at the octahedral. There's also some funky other shapes that come up when we have unshared pair of electrons around that central atom, like the sawhorse and the T-shape and linear, or square pyramidal and square planar, T-shape and linear there. But you're going to be more concerned about the upper ones on this. We okay to move forward? You got all that down? Okay, so now we're going to practice it. We've got to be able to look at a molecule and we've got to be able to name it and be able to tell me the angle. So, BCl2. Well, beryllium has how many around it? How many electrons? It's in the second column. Has 2. So it has 2 electrons that it can bond with. So it bonds with one chlorine on one side, one chlorine on the other side. What shape? Linear. What is the angle in a linear? 180. So you did that well. So if we look at boron, how many are around boron? How many electrons are around boron? 3. And I'm bonding with 3 different things, right? 3 chlorines. So there's no extra electrons there left out at all. So what shape am I going to make? Trigonal planar. What's the angle going to be? 120. So trigonal planar and 120. So now that we go to CH4, which is also known as methane gas, CH4 has 4 things, carbon in the center, 4 things around it. What shape am I going to make with that one? There's no unshared pairs of electrons. A tetrahedral. What's the angle on a tetrahedral? 109.5. Good. Trigonal planar means it's all in one plane. Okay, the next one that we're going to do has an unshared pair of electrons. Nitrogen won't share one of its shared electrons, but it will share 3 bonds with hydrogen. So it still has 4 things around it. Right, this one's going to be trigonal pyramidal because that nitrogen's pulled out of the plane by those unshared pairs of electrons. What are the angles now? 107 because it has 1 ghost. Okay, water. Water's going to be 105. What's the shape? Bent. Okay, so we should be able to look at this. If you have to draw it, draw it. But you need to know the angle, you need to know the shape of the molecule. Okay? These 3 things right here will help you determine what you've got. Does it have any lone pairs that are not shared? Those are the ghosts. Those are the unshared things. That's going to affect what kind of shape I'm making. How many are bonded? How many can I bond? Okay, those kind of things. All right, going forward. We need to talk a little bit about electronegativity. Electronegativity is how badly does something want an electron. Fluorine wants it pretty badly. And on this chart that's only to 2 sig figs, fluorine has electronegativity of 4 and francium 0.7. We're going to use a different chart here in just a minute. I didn't realize that they were off. The next chart has 3 significant figures where this one only has to the 10th place, so the other one has to the hundredths. But electronegativity is how badly do they want an electron. If you look at this, francium wants to get rid of them, so it doesn't want one very badly. But fluorine really wants an electron. Okay, so this is how I determine what type of bond I have. Okay, if we're playing games, we need to put them away. We need to be working on our notes. Okay, ionic is where we transfer the electrons, when the electrons were actually moved. It's a 1.9. So if I take the difference between the 2 elements and get a 1.9 or higher, I've got an ionic bond. If I have between 0.5 and 1.9, that's going to be a polar covalent, where it's not quite strong enough to rip the electron all the way off, but it's strong enough to have one side have a little bit more of the electrons than the other. If it's considered a non-polar, it's going to be less than 0.5, and this is according to your book. Some of them say 0.4 is the cutoff on the bottom, and some say 1.7 is on the top. So it just depends where the break point is, but that's where your book tells you it is. Okay, so when I'm talking about polar, tell me what this symbol is right here in math. Delta. What does delta mean in math? Change. That's a full change. We're going to use a partial change. A partial change is that, which is a lowercase delta. This is a negative. This is a slight positive. If I can take a molecule and I can split it with one line and I can have a slight negative and a slight positive, then I have a polar molecule. The bonds here between hydrogen and oxygen, the bond itself is polar. But I can have polar bonds and a nonpolar molecule. So I need to be able to determine, do I have polar bonds? Do I have a polar or nonpolar molecule? Water's easy because I can split it because it's bent. Let's look at a few others that are not so easy. So again, here's water. It's bent, so I can split it. This is polar. What about carbon dioxide? Can I get the positive away from the negative with one line? No, I can't. My negatives are on the outside and my positive is in the center. There's no way with one line I can cut it. This is a non-polar molecule, but it has polar bonds. Okay, you need to know that. So it has polar bonds, but it's a non-polar molecule. Looking at the next one right here, it already tells you it's overall polar. Well, overall polar because I can cut right here, and the carbon and hydrogen are considered the positive side, and the chlorine the negative side. So I have a pole, a positive and a negative pole. Over here, this says it's overall nonpolar. Why? Because the only thing that's positive is here in the center, and the chlorines around the outside are negative. So I can't, with one line, cut it away. I'm looking for something that's like a pill, where on one side I have a positive, and on the other side I have a negative, and I can see that definite side. That's polar. If I have something like this, where it has a positive in the center and the negatives are on the outside, I don't have a positive side and a negative side that I can cut away from each other. Okay, so this is a site I'm not going to go to right now, but I would suggest highly that you go to. It is a PhET, so if you want to write in your notes, it's PhET, and it's called molecule polarity. And if you just take a few minutes just to play with it, this will get set in your mind what polar molecules look like and what to look for polar molecules. I don't have enough time to do it with you right now, but I really would suggest that you do go there. This has some real molecules, and we'll look at some real molecules here in a minute. She puts some real molecules on the test. You want to be able to identify what's going on with those. This is a good place to go to do that. Okay? Going forward, let's try and figure out what type of bonds these are by using the electronegativity. To do this, I would say lithium is 0.9, fluorine is 3.98, so I go 3.98 minus 0.98 equals 3.0. So my difference is 3.0. Well, if I look here, above 1.7 is ionic. So I would say this is an ionic bond. Will you do the other three? Tell me what type of bond the other three are.
Does it matter which one's on top?
You want the bigger one on top because you want a positive number. Good question. You're just taking the difference in the two. If you're having a hard time finding it, I'm just going to circle real quick where they are. Those are the ones you're using.
So basically, if they're close to each other, they're going to be nonpolar.
For the most part, yes.
If they're across here,
Right. Okay, so if we take copper oxide, we would take 3.44 minus 1.90. Now I subtract it, 1.54, which is in that polar covalent area, right? If I take nitrogen and oxygen away from each other, 3.44 minus 3.04, I'm going to get 0.4, that says 4, 40. So 0.40 is what? Non-polar covalent. Okay, and the last one, hydrogen versus fluorine. we have 3.98, and that my thing's not working, 3.98 minus 2.20, we end up with 1.75. So that would be what? Ionic, right?
What was it? That's 1.78.
1.78? Oh, sorry, 1.78. It's because when I wrote it, it looked like a 5, but my pen doesn't work down there at the corner. Okay, so you should be able to do this. Given a chart, given a chemical formula, you should be able to subtract them. You will not have that division stuff on the test. You have to have it on your card or you have to have it memorized.
The division stuff.
Telling me where the division is from covalent to polar covalent to ionic.
Oh, like the numbers?
This one right here. Yeah. You won't have that. Okay, what you need to think about though is this is not a cutoff, straight cutoff. This is a continuum. So it's either more ionic or more covalent. Okay, so we're talking about a bond in that way. So we talked a little bit about polar bonds, polar molecules, nonpolar bonds, and nonpolar molecules. Nonpolar bonds would be if I'm right next to each other, like they were just saying, right next to each other, or the same element. Those would be nonpolar bonds. Nonpolar molecule can have polar bonds, but it's just arranged so I can't have a positive side and a negative side. Polar molecules have to have polar bonds, and they have to be arranged in such a way that I can cut it with one line and get one positive on one side and one negative on the other. Okay? We okay? All right, so let's see what you can think about this. Tell me if the molecule is polar or nonpolar. Tell me if the bonds are polar or nonpolar. HCl. Top one. Polar and, so bonds are polar. And the molecule, is it polar or nonpolar? So polar. Correct. Okay, what about NH3? Polar bonds or polar molecule or both? Polar molecule and bonds. Good. This one is tricky. They will show it to you like this, because that's how we would draw it, right? What do you need to remember? Good. The two dots here will pull the nitrogen out, and that makes it so I can split it. I got to remember that, okay? All right, what about boron trifluoride? Polar polar bonds or nonpolar bonds? Which one? No.
How do you tell what the bonds are?
So boron and fluorine. They're not close enough. If they're right next to each other, we can call them nonpolar. But these ones are not right next door to each other. Boron and fluorine are farther away. So polar bond, is the molecule polar or nonpolar? Nonpolar. Good. The molecule is nonpolar. What about carbon tetrachloride? Okay, talk about bonds first. Both nonpolar? Carbon and chlorine.
You said they're not next door.
They're not next door neighbors, so they're going to be a polar bond. Okay, what about molecule? Nonpolar, because I can't cut it away. Good. Okay, the next one is chloromethane. So chloromethane, polar bonds?
Yes.
Polar molecule?
No. Wait a second.
Yeah.
Yes.
It is yes, it's a polar molecule. Because here the carbon and the hydrogen make the positive side and the chlorine is the negative. Okay? All right, we're almost done. We okay?
How do we know that how do we know that it's positive?
If elements are right next to each other, so if I had a nitrogen and oxygen, I would say the bond is not polar. But the molecule is.
Yeah, but you said, can you go back one second?
I can go back.
So you said the one on the right, the carbon and the hydrogen make it positive. How do you know what's positive?
So I know this is usually a positive, 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 right?
How do you know
Because hydrogen wants to give one away, right? It usually gives one away. So it becomes positive. Carbon is like the neutral middle. So it just sort of stays neutral.
So we're going back to a thing where it's like, it's just positive, negative based on the
Yes.
Okay.
Okay? And then chlorine's going to gain one, so it's going to be my negative side, right? So it's not a real positive and negative, so I say this is my slightly and this is my slightly. Okay? All right, so going forward here. Now, she's going to take compounds that you might not have ever seen before. So we're going to take a few and we're going to look at them. You need to be able to look at that molecule and say, it's going to be polar. The bonds are polar, the molecule's polar. Or the bonds are polar, the molecule's nonpolar. Or the bonds are nonpolar, the molecule's nonpolar. Okay? So here is hydrogen peroxide, which if you did the Lewis dot, it would look something like that, right? And that looks like it what? Would be polar bonds, nonpolar bonds?
Non-polar
Polar and nonpolar.
bonds.
How? Why am I saying that?
Because the oxygen.
Oxygen and oxygen are bound to each other, so that bond right there is nonpolar, but the oxygen to the hydrogen is polar. So depending on which bond she points to or which bond she puts a number, what is number 1 bond? It would be a nonpolar. But if she said here, number 2, what's number 2's bond? Polar. Okay, see what I'm saying? Okay, you're saying it's polar. Okay, where are you going to cut it to get a positive and a negative?
Down in the middle.
Slim line.
I've got to get the oxygens away from the hydrogens.
Oh. You would have to.
This is what it actually looks like.
Oh, that's easy. You just go.
If you think about it, each of those oxygens is a tetrahedral shape. So you've got to picture it in your brain. It's a tetrahedral shape. And because it's a tetrahedral shape, these two hydrogens most likely are going to be in the same plane. Okay? So yes, I can cut this now right here. And because I can cut it right here, this is going to be my slight positive, and this will be my slight negative. So that is polar. Okay, she might give you something like this. I've given you a little hint here. The oxygens are more negative than the nitrogen is. The carbons are neutral, and that's where every
Wait, I don't even see
carbon would, they shortcut this. If you ever see any pharmacy things, this would be a carbon, that's a carbon. This is a carbon, 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 carbon. They just don't write them. They don't write them because it gets really monotonous and horrible when you get into big molecules. Every time there's a bend or an end, that's a carbon. Okay, so oxygens are negative. Nitrogen's getting more towards carbon, so it's not as negative. Is this molecule polar? Well,
But you said carbons are in the middle, right?
carbons are in the middle.
Okay, and where's
Okay, what about bonds? You got to be careful here, right? Because if she says, is this bond polar? Is this bond polar? Carbon versus nitrogen. It's not real polar, but yeah, well, they're next to each other. I probably would say no too. Okay, so this one would say no. What about if I said this one? Polar. What if I said this one? Polar, because it's more than one away. Good. What about the molecule? Polar or nonpolar? Nonpolar. Why do you say nonpolar?
There's more that are towards the negative side of the
Okay. There also is an oxygen on the top and an oxygen on the bottom. How am I going to cut them away with one line? Right? So this is a nonpolar molecule. Okay, going forward. Ethanol. This is drinking alcohol, and if I did the Lewis dot, this is what it would look like. And if I did a little bit better Lewis dot, this is what it would look like. If I did even better and I made the molecule of it, this is what it would look like. Does that make a difference in what you think the molecule is as far as polar or nonpolar? They're there.
Oh, I see. The red's oxygen.
Red is oxygen, black is carbon, white is hydrogen. Can you cut?
Yes.
You can.
Drink the red at the bottom.
So you're going to cut right here. Basically, this is my negative right here, and this side over here would be considered my positive. Okay, so that is a polar molecule. Now, acetaldehyde is what is made when you put methanol in your body and it goes through your stomach. This is that model. Polar or nonpolar? Very polar, because now I don't have to deal with any oxygens at all anywhere near it, and hydrogens anywhere near the oxygen, and that oxygen becomes even more negative. So that is even a more polar molecule. This in your body is what causes hangovers. It also is what causes liver damage, brain damage, and cancers. Yeah, don't drink. Okay, here's another one she might give you. This is a B6 vitamin. Look at this. Remembering, fluorine and oxygen are probably your most electronegative, meaning they're going to pull the negative.
All those other ones that aren't shown are carbons, right?
Right. Is this molecule polar or nonpolar? This one is actually polar. Look at this. If the oxygens are negative, I have a negative here, negative, 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 negative. Where do you see the negatives? On the top. So that means the bottom has more of a positive. So it's not real obvious. Yeah, it might not be left to right. It might be top to bottom. So if you have to think about, okay, where's the oxygens? Where are they at? That's going to pull my negative.
So even though the phosphorus is absolutely it's still the
Right.
So if you can cut it, it's polar, and if you can't cut it, it's non-polar.
Right. So here, this one would be cut right here.
And everything about that line is negative.
Is a slight negative. It's not total negative, it's a slight negative. So if I made a pill, this side would be the slightly negative side, this side would be the slightly positive side.
And the only reason those carbons that are not labeled can be cut is because they're plus or minus.
Yeah, carbons are neutral. So they're just like me and them there. Okay? All right, so that takes us through the end of the chapter. That's it. You have 15 minutes left. I want you to either do your pre-lab or do a Learn Smart. I want one of those two done before you finish the period. So next time I'm not going to be here. So next time you're working on Learn Smarts and homework and or the pre-lab. All of that needs to be done before I come back on Tuesday for the lab.
So we're doing this thing where the pre-lab should be done if you want to do the lab.
Right. The pre-lab has to be done before I will allow you back in lab. The lab will take the whole period. You don't want to sit in here doing your pre-lab.
Wait, when is the lab?
Tuesday. Friday is a work day. Friday, I want you to get all your homework, all your Learn Smarts, the pre-lab done. Make sure you read through the lab. The lab is in the lab book. This one is okay. It's not rough. Too bad. It has a lot of diagrams, and I didn't want to redo the diagrams. Okay? So, all right, going back a slide.
So the N on the bottom, though, isn't that negative?
It can be a little bit negative, but here the oxygens pull. You have a lot more oxygens on top. It's like one person's negative and a bunch of positive versus a lot of negative with little positive. So which side's more negative? Does it make sense?
Yeah, but I just don't understand how you can just decide that and then cut it down the middle. I'm just so lost.
Basically, look at it this way. This one right here is almost neutral. It's right next to a neutral, right? So it's basically, okay? These ones right here are definitely a slight negative, slight negative, slight negative, slight negative, slight negative. So if I look at that, I can say, okay, this whole top part has a slight negative. This bottom part has one that could be negative, but is not real strong. So because of that, I can have a positive negative side. Okay?
So what happens if it was more negative? Would you just have a non-polar?
If I had more oxygen down at the bottom, I would say no, it can't be, it's a nonpolar
Or
molecule.
what happens if the N is actually like an S? that nitrogen change to sulfur, so would it be?
So that would be nonpolar.
Okay. But then if it was phosphorus, would it be polar?
Phosphorus, it would be polar. Okay? So basically just the first two columns away from the noble gases will pull that electron more and give you that negative. All right, so we're working on pre-lab or Learn Smart. I want one of those two done before you leave today.
Do we get our pre-lab stamp this time?
Yes, you must have your pre-lab stamp to go into lab.
So we can get that today.
Yep, you can get it today.